So, what are we talking about today? We're talking about factoring and division, okay? Because as we saw last time, if we could find the zeros of the function, find the x-intercepts and the multiplicities, that gave us a lot of information about the graph. And so that's what we're going to be looking at today. So we start off with a little review here. The zeros of a function are the solutions to the equation f of x equals 0. All right. So zeros are what you plug into the function to get 0 out. A 0 corresponds to the x-intercepts. Okay, so that's the terminology. So to find zeros, we're going to be solving things that look like f of x equals 0. That's what we're going to be doing. Really, not only today, but all of next week, is we're going to be trying to solve a polynomial function equal to 0. And our main strategy is going to be to try to factor. Okay? And so the first couple examples, we kind of review a couple strategies from intermediate algebra. There's the concept of factoring by grouping and the idea of a quadratic in disguise. And so let's look at each of these. Look at the example here, 2x cubed minus 10x squared minus 3x plus 15. And you always want to double check here that you've got everything written down correctly, because as you know, with factoring with trinomials, one false move, you can get something that can't be done, or at least not nicely. Okay, so to find the zeros of this, we want to set this equal to 0, and we want to try to factor. Now notice we have 4 terms here. We got the 2x cubed, the 10x squared, the 3x, and the 15. We have 4 terms, so trying to unfoil it using the usual techniques isn't going to work. But we can try something called factoring by grouping. And factoring by grouping is you just group 2 terms at a time and try to factor out what's in common to just 2 of the terms. So here, there's a 2 coefficient I can factor out and an x squared. So if I factor those out, I'm going to be left with an x minus a 5. And what I'm trying to do here is factor something out, so I'm still left with an x minus 5. Let's see if the cat wants to go out. All right, she must have been late to her meeting outside. So what could I factor out here? If I factored out a 3, I'd have a minus x plus 5. But if I take out a negative 3, I'll be left with an x minus 5. Oops, equals 0. And I always suggest to students it only takes a second to double check the factoring. If I take the 2x squared times the x, that gets me back to the 2x cubed. If I take the 2x squared times the negative 5, that gets me back to the negative 10x squared. If I take the negative 3 times the positive x, that's the negative 3x. Negative 3 times negative 5 is the plus 15. So that works. And now I see that I have a quantity x minus 5 that I can factor out. And so we'll do that. Taking out a quantity here, I'm left with a 2x squared minus a 3. And now that I have it factored, I can set each factor equal to 0. So here's one factor, here's another factor. So I got x minus 5 equals to 0, or 2x cubed minus 3 equals to 0. So here I'd add 5 to both sides to solve it. X equals 5. Here I have a quadratic, but I don't have a middle term. I don't have an x term, so I can add 3 to both sides, get the x squared by itself, divide by the coefficient. X squared is 3 halves. To get the solution, I'm going to extract square roots. Now when you're solving and you extract the square root, you get the plus and the minus. So don't forget that. So we had a 3rd degree polynomial. We ended up with 3 roots. This one got counted once. Here we had a second degree equation, but we got 2 roots, so each of those are going to get counted once. So each of these have multiplicity 1. So any questions on this before we check it graphically here? Do you remember the factoring by grouping thing? If we can handle it with something we know from before, we want to do that before we break out these more sophisticated techniques we're going to learn here next couple days. So we got Desmos up here. We're going to graph p of x was 2x cubed minus 10x squared minus 3x plus 15. I think I did that right. Check out the roots here. So there's the 5. Now we had plus or minus square root of 3/2. So let's look at what that is. So I think we can, there we go, boom. So there's our x equals 5. There's the rounded version of the positive square root of 3/2, and then there's the rounded version of negative. And notice, if you zoom in here near each of these zeros, it looks like a line, and that's indicative of being multiplicity 1. All right, so that's a quick way to check our answer. And I recommend doing that. Anytime you do these problems, fire up Desmos, if it's, and check your answer. It helps reinforce the ideas here. Okay, let's look at this example. This is another one. It's got 4 terms. Now usually this would be a little project you'd work on in groups, but that's not how things are these days. So we're gonna do this together here. So I want to find the zeros. So find the zeros means I set it to 0. I have how many terms? 1, 2, 3, 4. Let's try the factor by grouping. I'm going to take out the x squared here. 2x cubed over x squared is 2x. Minus x squared over x squared is 1. And once again here, I could factor a 10 out, be left with a negative 2x plus 1, or I could factor out a negative 10 and then have the 2x minus 1. And once again, you can check if you multiplied back in that you get all the parts, and it only takes a second to do it. There it is. Okay. Now I look to see what's in common here. Now I've got that whole quantity 2x minus 1 I can factor out. And now that I have 2 things that are factored against 0, I know that one or the other has to be 0. So either the 2x minus 1 is 0, or the x squared minus 10 is 0. Add 1. 2x is 1, divide by 2. So again, x equals a half there. Or, you could add 10 to both sides. X squared is 10. X is plus or minus square root of 10. Thinking about multiplicities here, the 2x minus 1, that was one factor there, so that's multiplicity 1. And the x squared minus 10, that was, x had the power 2 on it, but then we got 2 different answers, so those are each multiplicity 1. So if we graph this thing, we should expect 3 separate x-intercepts, and since all the multiplicities are 1, it should be locally linear at those points. And the square root of 10 was the irrational root. So let's make sure we have a good approximation for that, 3.16-ish. So there's the negative square root 10, there's the half, there's the positive square root 10, and everything looks locally linear. Any questions on this example here? So if you have 4 terms, try to factor by grouping. It's usually quick to see if it's going to work, and if it does work, it's going to make your life a lot easier. Okay, the second thing we want to remind ourselves of are these things that I call quadratics in disguise. So remember, a quadratic looks like ax squared plus bx plus c is 0. So that's a quadratic equation. You've got x to the second power, and you may have x to the first power in there as well. So let's look at this example. X to the fourth minus x squared minus 12. We're trying to find the zeros of this, and it's not a quadratic because the highest power of x is not x squared, but rather x to the fourth. But it is what I call a quadratic in disguise. If you notice, what makes a quadratic is you've got that x squared there, and the other term is x to the first. So the power here is exactly twice what it is here, and you have exactly 3 terms. When you have that, you can try to unfoil that trinomial by splitting the x part up and then guessing and checking with factors of the constant term. Here, we've got 3 terms. And the exponent here isn't 2, but it's 4, which is exactly twice the exponent here. Okay? So that means that it's not a quadratic, but it's a quadratic in disguise, meaning I can kind of treat it as a quadratic. Okay? I can think of this, split this up into x squared and x squared. So I can just cut that exponent in half and then try to find factors of negative 12 that add up to negative 1. And so I could do that with a negative 4 and a positive 3. And I can check here, my handiwork, x squared times x squared is going to give me x to the fourth. Here, this gives me a positive 3x squared. This gives me a negative 4x squared. And that gives me a negative 12. Okay? So quadratic in disguise, you need to have 3 terms. And the exponent on one of the terms is twice the other. If you have those 2 conditions, you got yourself a quadratic in disguise, so you can treat it like a quadratic. In this case, it factored nicely. Setting each factor equal to 0 gives us an honest-to-goodness quadratic. We could add 4 to both sides here. Extract square roots. Don't forget the plus or minus. This happens to be a square root we can simplify to plus or minus 2. Here, we subtract 3 from both sides, and when we go to take the square root, well, it's a non-real number. You may remember these are imaginary numbers. We'll talk more about them at the end of the chapter. So a week from today, we'll have to review what these things are. This is not a real number. And today and on Tuesday, we're going to be concerned only with real number answers because those are the ones we can check on the graph. So we had a 4th degree polynomial. We ended up with 2 real answers coming from this quantity, so multiplicity 1 each. We had 2 non-real answers, multiplicity 1. But we're not going to be able to see those on the graph. So let's graph it and check our answer here. So I think that was called q of x, x to the fourth, minus x minus 12. Or was it plus x? What did I factor it wrong? Oh, I forgot the squared. There we go. Boom. There they are. So those other two answers are imaginary numbers. They're not going to show up because we're looking at the real numbers there. And there they are. And locally they look linear. Each has multiplicity 1. So here we go. F of t is t to the 4th minus 8t squared plus 15. Once again, if I set this to 0, I notice that the exponent here is exactly twice the other one. We've got exactly 3 terms. So it's a quadratic in disguise. So we can split this and try to see if we can get it to work out. Factors of 15 that add up to negative 8. We can do a negative 3 and a negative 5. Now I have 2 things factored that give me 0. I set each factor to 0. Add the 3 over. Add the 5 over. Extract square roots. Don't forget the plus or minus. We had a 4th degree polynomial. We ended up with how many answers? 4 answers. Let's graph it. See what we have. Answers involve the square root of 3 and the square root of 5. So let's get those decimals up for reference. Zoom in a little bit. There's the 4 intercepts we expect. And they've got the decimal equivalents of the square roots. Okay. Once again, locally, everything looks linear. That indicates multiplicity 1. So it checks. All right, so factoring by grouping, quadratics in disguise, these are things that are some more advanced techniques. They typically get shared. If you want more review of those, there's some in the homework, but I can also direct you to some additional practice in the appendix. All right, so suppose we've got a function that doesn't factor using what you learned from intermediate algebra. So it's not a nice trinomial you can unfoil. It's not a quadratic to use quadratic formula on. There's no factoring by grouping. That doesn't work. It's not a quadratic in disguise. Well, here's what we're going to try to do. We're going to try to factor, but let's remind ourselves the connection between factoring and division. So suppose I said I wanted to factor. Say I wanted to factor the number 126. All right. So typically what you do is you know some rules from arithmetic saying, well, it's an even number, right? So that's an even number. So I'm guaranteed that that's going to break down as 2 times something, right? And how do you figure out what that something is? Well, you divide 2 into that something. And then you check that when you divide 2 into it, you get remainder 0, right? So I'll put a little smiley face there. This is 2 times 63. So you check the factoring by doing the division. And now you know that 2 is there. We don't need to worry him anymore. Now we try to factor 63. And you say, okay, well, 63, 6 plus 3 is 9. I know 3 goes into that. To see it's 3 times what? You do what? Divide. And you get a remainder of 0. So it's 3 times 21. So you got your 2, you got your 3. These are primes. You can't break those down any further. And now 21, you may remember, oh, well, that's 3 times 7. And so you get 126, broken down as far as you can get it, is to 2 times 3 squared times 7. All right, we broke it down to its primes where you can't break it down anymore. And so this is going to be our strategy here. We're going to try to mimic this for polynomial functions. We're going to start off with a polynomial. We don't know how to factor. And we'll try to use information to help us break it down. And as we go, we'll use division to help us. Okay? So let's look at the polynomial here. X cubed plus 4x squared minus 5x minus 14. And I forgot what it is already. Oops. So that's what we're looking at. 4, negative 5, negative 14. All right. So let's take a look at that. Let's take that for a whirl here on Desmos. Go. Zoom out. Now, not surprisingly, since we have an x cubed leading term, we know that the end behavior is S-shaped. Since it's a positive x cubed, it's going to be an increasing S once I zoom out. So there we go. And we got some intercepts here. So we got some crazy decimal there. I don't know what that is. We got some crazy decimal there. I don't know what that is. But that looks like x equals 2 is a 0. So that looks like x equals 2 is a winner. Okay, so let's think about how that's going to fit in with this function. If I'm trying to solve p of x equals 0 to find all the zeros, then I would set this equal to 0. And since, and then I would try to factor, right? So at this point I try to factor. At this point I try to factor. Now, in order for x equals 2 to be a solution, that had to come from x minus 2 equaling 0. And the only way I would be setting x minus 2 equal to 0 is if I had an x minus 2 times something. You follow? Because that's what we do, is we factor and then we set each factor equal to 0. So you see I'm trying to reverse the logic here? Now why am I using x equals 2? Well, because when I looked at the graph, that seemed to be the only number that wasn't some crazy decimal approximation. So it's kind of like when we factored down the number 126. I knew that 2 was a factor there because it was an even number, and I could divide in to get the missing factor using division. So that's what I want to do, is I want to divide x minus 2 into this polynomial to get the missing factor. Okay? Now, whoops, let's get that out of there. How do you do that? How do you do that? This is how you would do that. You would take x minus 2 into the polynomial and work it down. This is polynomial long division. All right? This is too much to take in on a day like this. This is too much, right? It's a sleepy day. We need a faster, more efficient way to do this kind of calculation. And that's what I'm going to teach you. It's called synthetic division. Now, we go to great pains here in the handout and in the book showing you where synthetic division comes from. Synthetic division, it's called synthetic division because we'll be adding instead of subtracting. But what it does is it just helps us organize the division. And then it ends up making it extremely efficient to do because we're going to be doing a lot of this. All right. So this is how we're going to take care of this division problem. But first off, do you see why we need the division problem? So this is how it's going to work. So we need and I apologize, my memory is not what it used to be. We need to take x minus 2 into x cubed plus 4x squared minus 5x minus 14. All right. If I want to take it back to kind of visualize what's happening here in terms of the factoring, when we had the numbers there, I'm claiming that this factors into x minus 2 times something. And what's my guess there is because of how intercepts seem to work, okay? There's actually a theorem we'll talk about at the end of class that guarantees that always happens. So how do I do this? Well, here's what we're going to do. We're going to do what's called synthetic division. And this is more or less it's a streamlined version of regular division. Right, streamlined. Here's what we do. You see how it says x minus 2 here? Okay, x minus 2 corresponds to the real number x equals 2. So the first thing we're going to do is we're just going to flip that. In regular division, you'd be multiplying the negative 2 and then subtracting all the time. Well, if you multiply by negative 2 and subtract, that's the same as just adding with positive 2. So we're going to reverse the sign here. Instead of x minus 2, we'll put a 2 here. And then we're just going to copy down the coefficients. We've got 1x cubed, 4x squared, minus 5x, minus 14. When you do long division with polynomials, you always make sure you line up the corresponding powers of x. So we can take advantage of that by just keeping everything nice and neat and lined up here. The first step in synthetic division is always to bring down the first coefficient. I used to call this the Price is Right step because on the game show Price is Right, they told people to come on down. But I don't know if that show even exists anymore. Okay? You bring down the 1, and now we're going to do two things over and over again. We're going to multiply, and we're going to add until we're done. So we're going to multiply 2 times 1, and then that's going to be a 2. And then I'm going to add to give me 6. And then 2 times 6 is 12. And then we're going to add to get 7. And then 2 times 7 is 14. And we're going to add and get 0. And we're going to put a little smiley face in that 0. Whoops, because what's in that 0 turns out to be the remainder. And what this says is that if you take x minus 2 and divide it into this, you're going to start with 1x squared plus 6x plus 7 with the remainder of 0. So these numbers here correspond to the coefficients of the quotient polynomial. Since we're taking an x and dividing it into an x cubed, we're going to be left with an x squared. Now, if you're interested into where this comes from, like I said, we've got a very detailed derivation both in the handout and in the book. Experience has taught me that the students that really want to see it will take the time on their own. It doesn't get too technical. It just can be overwhelming. So there it is. And we're gonna be doing this again and again and again. Okay. So after I do it and you watch a few times, you'll be able to do it. But that's pretty much all it is. Synthetic division works as long as you've got something of the form x minus c into some polynomial p of x. You can use synthetic division. You need to have this be coefficient 1, though, for that to work. If it's not, you just factor and factor it out. So returning to our problem at hand, right, we were trying to set x cubed plus 4x squared minus 5x minus 14 equal to 0. We suspected x minus 2 was a factor based on the graph. The graph suggested 2 was an x-intercept. And we found out that it actually is x squared then plus 6x plus 7. So now that we factored it, we can set each factor to 0. X minus 2 is 0, or x squared plus 6x plus 7 is 0. Here we got x equals 2. No surprise there. And here we have a quadratic. Now we can try to factor this quadratic. Doesn't seem to factor. So if it doesn't factor, we can run it through quadratic formula. And that's not unexpected, because when we graphed that function, 2 of the x-intercepts seem to be Wiley decimals. Okay, so that's kind of where these decimals are going to come from. So I always start quadratic formula with the discriminant to see what I'm dealing with here. So b here is 6 minus 4ac. Oh, welcome in. Welcome in, Jacob. So that's a 36 minus a 28. That gives us a 12. No, it doesn't give us a 12. Hold on. It doesn't give us a 12. It gives us a what? An 8. And so my x here would be the opposite of b. So the negative 6 plus or minus the square root of 8, all divided by 2. And we want to go ahead and simplify that. Negative 6 plus or minus, and remember how we simplify square roots. I look for perfect square factors. So the square root of 8, that's the square root of 4 times the square root of 2. So that's a 2 root 2 over 2. And remember how we can simplify these is divide each of these by 2. So that's a minus 6 over 2 plus or minus a 2 root 2 over 2. That's minus 3 plus or minus root 2. So remember, this is shorthand for two different answers. We got our x equals negative 3 plus root 2, and our x equals negative 3 minus root 2. So any questions? Once we get that missing factor from the division, any questions on getting the quadratic there? So we started with the third degree polynomial. In this case, we got 3 individual zeros. We expect each of these to have multiplicity 1. So let's check on Desmos. So we already have the graph up on Desmos, which is nice, but now let's check out the decimal approximations with the negative 3 and whatnot. So negative 3 plus square root 2 and negative 3 minus square root 2. So let's check it out. There's a negative 4.414-ish. That's this one. There's the negative 1.5. And there's 2. And locally, all these things look linear, so multiplicity 1. So this example is how we're going to be working these problems, not just today, but also on Tuesday. We're going to be trying to find the zeros of a polynomial. We're going to throw it in Desmos, and we're going to look for friendly values. In this case, 2 was a friendly number, and we're going to divide by that 0. to help us knock down the polynomial to help partially factor it. Our goal is to get it into something that we can factor from before. So either it's a trinomial we can unfoil, or factoring by grouping, or quadratic in disguise. A quadratic we can use the quadratic formula on. If not, we'll keep going until we get it into one of those situations. Okay? So this example is representative of the process we're going to be doing for the next couple of days. All right, so we got a couple examples here just to practice the synthetic division. So let's just practice the synthetic division here. So if we graphed, let's do the division. So once again, the division problem this indicates is x minus 3 dividing into 5x cubed minus 2x squared plus 1. Excuse me. So to do this with synthetic division, we take the opposite. It says x minus 3, so we're going to start with 3. And then we record the coefficients of the powers of x. So in this case, we've got 5x cubes. And we've got minus 2x squareds. But notice we don't have any what? X to the first term. So we're going to put a placeholder in there, 0 for 0 x's, and then 1. And you may remember the placeholder idea from regular long division. Okay. First step, bring down the 5. And now, so we multiply and add. 3 times 5 is 15. Negative 2 plus 15 is 13. 3 times 13 is 39. 0 plus 39 is 39. 3 times 39, that's what? 90 and 27. So, let's do 3 times 40 minus 3. That's easier. So what, 1187 plus 1 is 118. Okay? So the quotient here, so if I were to write this out, the quotient would be 5x squared plus 13x plus 39. The remainder would be 118. Okay. Now in this case, the remainder is not 0, so I can't partially factor it with the remainder 0. But here's what I could do. This means that 5x cubed minus 2x squared plus 1 looks like x minus 3 times 5x squared plus 13x plus 39 plus 118. If that remainder were 0, it zeroes out. Did you hear something outside?
Yeah. Is it moving up?
Maybe. Could you go check? Okay. All right. So notice something here. Even though I didn't get a remainder of 0, what would happen if I plugged in x equals 3 into that function? That's the same as plugging x equals 3 into here, which would completely zero that out, which would then take that 0 with it, and I'd be left with what? 118. So let's test that out with Desmos. So do the p of x is 5x cubed minus 2x squared plus 1. Now let's plug in 3. And look at that, we get 118. So even though that remainder wasn't 0, which would have told us we found an x-intercept, the remainder matched the function value. And once again, that's something called the remainder theorem we're going to be talking about here at the end of class. All right, let's try this division once again. Let's first rewrite what this means. We would be taking t plus 2 into t cubed plus 8. And so we're going to take the opposite there, 2. Instead of 2, we're going to write negative 2 then. And we're going to record the coefficients here of the powers of t. So we've got 1t cubed. There's no t squared. There's no t, but there's an 8. So notice here we're having two placeholders. Be helpful if I write this out perhaps. All right. Step 1, bring down the 1. And now we multiply and add. Multiply and add. Multiply and add. And guess what, folks? We got ourselves a winner. So we got a remainder 0. So this tells us that if I do this division, I'm going to get t squared minus 2t plus 4 with the remainder of 0. Or in other words, t cubed plus 8 is equal to t plus 2 times t squared minus 2t plus 4. And, depending on, how exhaustive your intermediate algebra was, that's the sum of cubes factorization. But if you forgot about it, then here it is for us using synthetic division. So this shows that negative 2 has a remainder of 0. That means that negative 2 is a 0 of the function. And sure enough, if I check this on Desmos, look at p of negative 2. Boom, at 0. You can see it crosses there at negative 2. Okay, so here's the remainder theorem and factor theorem we talked about. The remainder theorem says if you take x minus c and divide that into a polynomial p of x, and you get some remainder equal to r, then this says that p of x can be partially factored as an x minus c times some other polynomial we'll call q of x plus r. That's the division algorithm. And that means that when you plug c into it, you get c minus c q of c plus r. That's always going to zero out, and you'll be left with r. So p of c equals r, which is the remainder you get when you divide p of x by x minus r, or x minus c. All right? So in particular, if r equals 0, that means p of c is 0, and that means that your polynomial looks like x minus c times q of x plus 0. Okay? And so you've partially factored the polynomial. So the remainder theorem, this is the remainder theorem, and then this is called the factor theorem. All right? And theorems are mathematical tools in the background that justify the things that we're doing. So anytime you have an algorithm in mathematics, or here's how we're going to do this, there's a theorem in the background that's telling you you're guaranteed this will work all the time. So going back a couple of examples, when we had the graph and it looked like we had an x-intercept at 2, the fact that 2 worked guaranteed we'd be able to factor the polynomial as an x minus 2 times something else. So that's the factor theorem. All right, so here's the big takeaway. X-intercepts correspond to zeros. Zeros correspond to factors. So if 5, 0 is on the graph, that means that your polynomial has to factor x minus 5 times something, and vice versa. Okay? All right. So let's continue here with these examples. So here's a polynomial. It's a 4th degree polynomial. Let's say p of x is equal to 4x to the 4th minus 4x cubed minus 11x squared plus 12x minus 3. Right? Let's dial this into Desmos and see what we can see. We got a lot going on here, folks. Now we're interested in x-intercepts. So let's zoom in a little bit. We got some kind of wily decimal here. I don't know what that is. I got 0.50 and I got what? Some other decimal. Okay? Now 0.5 is a decimal you understand, right? 0.5 aka 1/2. And what do you notice about that 0.5? See, these decimals here, locally they're linear. That indicates a multiplicity 1. Locally that looks like multiplicity 2. So it looks like the half should divide in twice. You follow? Should divide in twice. Kind of like in our original arithmetic example, we were factoring 126. 3 went in twice. You follow? 3 was a double factor there. So let's work this out here. So let's try x equals 1/2. So from the graph, x equals 1/2 appears to be multiplicity 2 because it bounced there, right? Locally looked like a parabola. Okay? Locally looked like a parabola. So here's how we're going to see that. We're going to first we got to divide 1/2 to see if it works. So we got the 1/2. We got the 4, the minus 4, the minus 11, the 12, the minus 3. All powers of x are represented here, so we don't need to have any placeholders. So first step, as always, bring down the first one. And now we're going to multiply and add. 1/2 times 4 is 2. We're going to add that. Negative 4 plus 2, negative 2. Multiply and add. 1/2 times negative 2 is negative 1. Negative 11 minus 1 is negative 12. Multiply and add. 1/2 times negative 12 is negative 6. 12 plus negative 6 is 6. Multiply and add. 1/2 times 6 is 3. Negative 3 plus 3 is a winner. We got a 0. And once again, you always want to put a smiley face in that 0 to indicate the joy that we found a 0. We found an x-intercept. So this confirms what we saw on the graph, that 1/2 0 is an x-intercept. Now we want to see if it works twice. So how do I do that? So if I think back to the factor tree, and once again, this is not something you need to write down. I'm just trying to write it here to connect all the concepts together. So forgive me for having garbage memory here. you go. So here's what we've shown. With this division here, here's what we've shown. We've shown that x equals 1/2 is a 0. That comes from, so if x equals 1/2 is a 0, that comes from x minus 1/2 equaling 0, which came from an x minus 1/2 factor. And we've shown that it's x minus 1/2 times something. What's that something? 4x cubed minus 2x squared minus 12x plus 6. All right? Now, if I want to show that x minus 1/2 goes in twice, I need to show that x minus 1/2 goes into this factor. You follow? Just like when I had the original arithmetic example, we would divide out, we divided out the 2, and then we looked at what's left over. It's the same thing. So I'm not going to divide 1/2 into the original again. I already know it goes in. I need to divide it into this one. So we can just extend the table and take 1/2 and just extend it here. You follow? Bring down the 4 and multiply. 1/2 of 4 is 2. Add. Multiply. Add. Multiply. Add. So now what I've shown is that this is 4x squared plus 0x minus 12. So remember, all I was doing was setting this equal to 0. So notice after the first division, we divided out an x, we're left with x squared. After the second division, we divided out another x to get down to first division got us to x cubed, second division got us to x squared. And now we can see that we've got x minus 1/2 quantity squared and 4x squared minus 12, and now we're ready to go. Set each of these factors equal to 0. Here's our x equals 1/2 with the multiplicity of 2 that we expected because of that exponent there. Here we can add the 12 to both sides, divide the 4 to both sides, and extract square roots. So don't forget the plus or minus. Now, once again, you don't need to write this down. I just put this here to try to connect it with what we were doing earlier with that numerical example. You can actually get this right from here. You've got the x minus 1/2 going in twice. You started with fourth degree polynomial. You knocked it down by 2 powers of x. That would be a 4x squared plus a 0x minus 12. Okay? Are there any questions on the mechanics of synthetic division or how it helps you factor? Now, this was a quadratic. We got 2 separate answers, so each of those answers should be multiplicity 1. Going back to Desmos, let's type in square root of 3. Sure enough, that's these wily decimals here. So there's our 1/2 multiplicity 2 looking like a parabola. Here's the negative square root 3 looking linear, and the positive square root 3 looking linear. Okay? All right, let's look at this one. We've got p of x, 2x to the 4th, plus 11x cubed, plus 11x squared, minus 15, minus 9. So it's 2, 11, 11, negative 15, negative 9. Let's get down there. Oh, minus 15, minus 9, of course. There we go. Get that out of there. Okay. So here's our polynomial. It's a fourth degree polynomial. That means it's the end behavior is U-shaped. It's an upwards facing U. Here we go. There. We got the X. All right. So here's what we got going on here. End behavior is at upward facing U. What do we got? We got negative 3 there, and notice it bounces. And then we've got what? Whoops. Looks like negative 1/2. Looks like 1. Now remember what the goal here is, folks, is we want to find all those zeros and multiplicity. So it's up to you which one we want to start with. Those are all fairly friendly numbers. We're not getting crazy decimals out of that. We could start with the negative 3. Knock it down. We could start with the negative 1/2. We could start with the positive 1. Just like when you factor a number down, it doesn't matter how you factor it. As long as you keep going, you'll get the same prime factorization at the end. Same thing's going to happen with these polynomials. Let's work with the negative 3 since it looks like that goes in twice. That's a 2-for-1 deal. And I'm all about bargains here. So let's try the negative 3. So once again, we're going to plug in. I've got 2x to the fourths, 11x cubes, 11x squareds, negative 15x is minus 9. All powers of x are present and accounted for. No need for any placeholders. Bring down the 2. Multiply and add. Multiply and add. Multiply and add. Multiply and add. Let's try negative 3 again. Bring down the 2. Multiply and add. You getting the hang of the synthetic division? Now at this point, let's see what we got left over. We've got x minus negative 3. In other words, we've got x plus 3 quantity squared. And then 2x squared minus x minus 1. So we factored it down. Remember, if we can get it down to a quadratic, we're golden. Because even if the quadratic doesn't factor nice, we could always run it through quadratic formula. So we split this up. We either get x plus 3 squared is 0. So there's our x equals negative 3 with the multiplicity of 2. Can I factor this nicely? 2x squared minus x minus 1. The graph suggests I should be able to, because we got friendly x-intercepts there. Whoops. Nope. Factors of 1. So this gives us a 2x plus 1 is 0. Or an x minus 1 is 0. Here's our x equals 1. And look what this gives us. Subtract the 1, divide by 2. That gives us the minus 1/2. And so there's all of them. The negative 1/2 and the 1 each came out once. Multiplicity 1. The graph should look locally linear there. Multiplicity 2 there for the x plus 3 should look locally parabolic. And that's what we're seeing on Desmos. Okay. Do you see how all this is tying together with what we did on Tuesday? So the end behavior theorem, the results about even and odd graphs, S shape versus U shape versus linear shape, all that stuff is back to help us. Any questions on this example? Remember the zeros, since x equals 3 is a 0, it comes from the quantity x plus 3. So we always divide in the zeros here. We always divide in the x-intercepts. Now, something you can do in the privacy of your own home, it'd be very instructive, is to start with this polynomial and divide out the negative 1/2 and divide out the 1 and see that you're going to get a polynomial that'll give you x equals negative 3 multiplicity 2. All right. Or maybe do negative 3 and then do 1 and then show that the polynomial you get will give you your minus 1/2 and the other negative 3. You follow? It shouldn't matter which order you discover the zeros and which order you divide them out. At the end of the day, you should get everything you're looking for. Just like when you factor a number, you get that prime factorization. It doesn't matter the order in which you do it. You're going to get the same primes to the same powers. Yes, Rooney, I know. And that's it. Okay, so that's this section. Once again, the take-home that's due next week, you can actually have everything you need from Tuesday. That's really just on Tuesday. The stuff we showcased here, we're going to build upon it on Tuesday. So we're going to get a couple more theorems to help us figure out where the x-intercepts can be. As soon as we get some good guesses for the x-intercepts, though, we're going to be right back and doing synthetic division and factoring and all that good stuff.